In this video, I will talk about splitting methods, which are a class of methods which can be used to compute the solution of a system of linear equations. Hi, my name is Frank and welcome on my channel. Let's start with a system with n variables and n equations, which are coupled in the linear way. You can see them here. So a11 times x1 plus a1n times xn equals bn, and so on. So we have n equations and n variables. The question is, how does a possible algorithm may look like which finds the solution to, or which computes the solution to this system? To be precise, we will talk about so-called splitting methods, which includes the so-called Jacobi method, Gauss-Seidel method, and the SOR method. In fact, we will start with the more general framework and then come to the more special parts. So we will put them in the general framework, which helps them to analyze such methods. Since this is a more advanced method, more advanced video, you should have a basic understanding of linear algebra. You should have heard analysis 1 or maybe 2. So you should know what the Banach fixed point theorem is and how to apply it. And it is good to know stuff about optimization and its associated numerical methods like the gradient descent method or the quasi-Newton method. To start, we're gonna rewrite the problem. So our n linear equations, they of course can be reformulated as a matrix vector multiplication. So let's define our vector our matrix A to be the matrix of the coefficient you've seen in linear equations. So it contains just a11 up to a(n). X is the vector we are looking for, and B contains the coefficient of the right-hand side. And then, of course, the n linear equations can be rewritten as a matrix vector multiplication, A times X equals B, with A being the quadratic matrix. I've mentioned in the introduction that we will gonna need the Banach fixed point theorem. This might look a bit arbitrary here, but you'll see in a moment that this is a very useful method and a very useful technique to analyze such splitting methods. Let's take a look at this theorem. We'll need a function f going from the space Rn to Rn in such a way that the difference of the mapping, so f of x minus f applied to y in the space in a norm of Rn, should be less or equal than a constant c, and it's important that c is a coefficient between 0 and 1 is not included, times the difference of x and y. If this equation holds for all x and for all y in the space Rn, then such a mapping is called a contradiction. And this contradiction can be used to actually prove that there exists not only a fixed point but also a unique fixed point x star. So being a fixed point means that f applied to x star is equal to x star. So this is a very strong condition. And furthermore, we do not also know there exists a unique fixed point, we also know how to compute it. This is a very, very useful technique. Let's start with an arbitrary element x0, which is randomly chosen, and we define the following sequence. So xk plus 1 is f applied to xk. Then we know that the limit of this sequence is x star. So this is a way to actually find the fixed point. And if we are now able to reformulate our problem to a fixed point problem, then we actually can compute the solution to our problem just by applying this recursive iteration here. And this is exactly what we're gonna do now, of course. We start with an invertible matrix, let's call it P. Then of course we know that A is P plus A minus P, just P cancels out. Might look very stupid here, but in fact, let's transform our system A times X equal B by replacing A with P plus A minus P. Bring A minus P to the other side. So it's there P minus A times X plus B. Reformulate some terms. So we have Px is Px minus B minus Ax. And now we know that P is an invertible matrix. So we can bring P from the left-hand side to the right-hand side of our equation. And we will end up with X being x plus p minus 1, so the inverse of p, times b minus ax. And of course, this is a fixed point equation because x is here, and here is some function applied to x. And using the construction from the Banach fixed point theorem, we know that the following sequence, so if you call the right-hand side here f of x, then we know that is that a sequence defined by xk plus 1 equals f of x, which is which is xk plus the inverse of p times b minus ax. This, and if this is a contraction, of course, this will converge to our solution of ax equals b. So this is a very good starting point to get a method out of it. And this is exactly what we will use throughout this video. Why is it called splitting method? Because the process of reformulating a equal p plus a minus p, this is called splitting. So we split the matrix into two parts, so basically p and, well, what's ever left, so a minus p. This is called a splitting for obvious reason, and the resulting methods are therefore called splitting methods. And the trick is now to choose p in a suitable way to get some nice methods out of it. Just a small remark. You can see here the splitting method again. We can reformulate this a little bit just by introducing the variable rk, which is thus b minus ax. If rk is 0, then we know that b is ax. So that's why rk is called is the residuum. And if we reformulate this a little bit, then we know that xk plus 1 minus xk is actually p minus 1 times the residuum. So the trick is to find a suitable p such the residuum goes to 0. Before we start with some specific examples of how to choose the matrix P, let's get a little bit a deeper understanding what's actually going on here. So for the following theorem, we assume that A is a symmetric and invertible matrix. Then we know that the solution x star to the optimization problem, we minimize x transposed ax minus b transposed x, which is a real number, it's a real number here, that this solution satisfies ax star equals b. So this is the system we're looking at, we want to find a solution for. The proof is quite easy. Let's define this thing here to be fx. We know that x star is the solution, so we know that the first order optimality conditions, which are just f prime at x star equals 0, or the gradient of f must be 0 at this point. This must be satisfied. And if you do a quick calculation using that A is symmetric, we know that the gradient of f is just ax minus b. And if the gradient is 0, then ax minus b must be 0, and this finishes the proof. In fact, this is not also a necessary condition, this is also a sufficient condition, just because this is a convex problem, which means that the first order optimality conditions are also sufficient. Just as a small remark, we only need the necessity of the first order optimality conditions. So throughout the next slides, keep in mind that our system can be formulated as an optimization problem, or to be more precise, as the first order optimality conditions for the minimization problem. But if you think about how to find solutions of optimality conditions, you usually search for points which satisfies the first order optimality conditions. And if we go a little bit deeper, let's start. Here's a quick example how this may look like. Of course, this is a one-dimensional example, so A is just 1, which is a 1 times 1 matrix, so quite boring matrix actually. B is chosen to be 3. Then the solution to ax equals b is, of course, x star equals 3, of course. And the function we want to minimize looks like this. So this is 1/2 x times x minus 3x. And if you plot this in a graph, the blue line is f of x. So the blue line is this term here. And the minimum of this function is, of course, by construction, we just proved it, at the point x star equals 3. So this kind of is a visualization of the optimization problem. But of course, we are going to do it in more dimensions, but therefore it's harder to visualize it. I already mentioned that we need a gradient descent. So why do we need a gradient descent? This is quite easy to see. So let's hop into the gradient descent. As already known, we know that the gradient of this function f here is ax minus b. And the general gradient descent looks like this. We start with x0 given, and then we compute xk plus 1 is xk minus a correction term. And the correction term is given by some step size theta times the gradient of f of x in the negative direction. So we go into the direction of the steepest descent. Recall that the gradient points into the direction of the greatest ascent, so putting the minus in front of it gives us the direction of the greatest descent. And this actually looks very similar to our optimization, to our splitting method, which you can see here. If we choose p to be the identity, and using that the gradient of this function here is ax minus b, we know that these two terms are actually the same. So what does this mean? This means that for the specific choice of p equals a, p equals the identity, the splitting method or the resulting splitter method can be interpreted as the gradient descent with fixed step size equals 1 for this optimization problem, for this function here. And this is quite interesting because now we have put two completely different methods into perspective. I mean, the derivation was completely different. I mean, the gradient descent is, well, if you want to put it that way, is an algorithmic interpretation going into the direction of the steepest descent, while the splitting method more or less can be constructed using the Banach fixed point theorem and some splitting. But still, for the specific choice, they're the same. Before we move on with the splitting methods, let's quickly take a look at Newton's method for optimization problems. So we want to find the solution to minimizing f of x. To do so, we start with x0 given and compute the next iterate xk plus 1 to be xk minus the inverse of the second derivative of f applied at xk times f prime evaluated at xk. For our specific problem, we choose f to be again ax minus bx, and we compute the first and second derivative. You can see them here. So f prime of x is ax minus b, and the second derivative is just a. If you plug in these values into the Newton's method, in the general formulation of the Newton's method here, well, you end up with this formulation here. So xk plus 1 is xk minus inverse of a times ax minus b. Can we put this into our general framework for the splitting methods? Of course we can. You can see it here. And if we choose p to be equal a, we obtain Newton's method. You can just see it here. However, this is of course, I mean, applying Newton's method for a linear system is quite an overkill for two reasons. The first reason is, of course, Newton's method will converge in one step, which is super nice. But second, we have to compute the inverse of the matrix A, because we'll need the inverse of the second derivative you can see here. But if we have to compute the inverse of the matrix A, well, of course, we can just compute the solution to our problem directly. So it's quite an overkill. I just want to put it here into perspective. We have now seen two extreme values for p. P chosen to be the identity will give us the greatest descent method. P to be chosen the matrix A will give us Newton's method. What if we choose P to be something in the middle? And this is the idea of this slide here. So let's start with the table here. Here you can see what happens if we choose P to be different values. The idea is the matrix P should be a good approximation of the matrix A with the property that it is easily invertible. So if you choose P in a different way, this will give us a so-called quasi-Newton method. Let's take a look at this table here. If you choose P to be the identity, of course, then the matrix P is super easy to be inverted, but it's a very poor approximation of A. On the other hand, if you choose P to be A, this is a very, very good approximation. In fact, this is the best approximation of A. However, it might be easily to invert. So for something chosen in the middle, whatever this means, this will be made clearer on the next slides, we'll end up with the quasi-Newton method for solving this optimization problem. And this is a very good, or in my eyes, it's in my opinion, this is a very good overview, a very good interpretation, in fact, of the splitting method, to interpret it as optimization methods or to algorithms for solving optimization problems. And in the following, we will now get into some actual methods, because nobody will compute the splitting method in such a way. Because then you have such a matrix vector formulation, you have to invert P. This is not suitable. But in the following, I will present you three different methods, which are splitting methods, and I will show you how to put them into our general framework. For the derivation of the examples, it's very useful to have the following splitting of the matrix A. So we split A into three different parts. So the first part is called the matrix D. This is just the matrix containing all the diagonal elements. So D is just a diagonal matrix. L is a strict lower triangular matrix. It contains all the elements which are below the diagonal. And similar, U is a strict upper triangular matrix. It contains every element which lies above the diagonal. Keep this splitting, or keep this reformulation in mind, because this is very useful for analyzing the next algorithms. For our first algorithm, the so-called Jacobi method, consider again our n linear equations, now here in this full form. And the idea of the Jacobi method is, okay, we take the ith equation and solve it also for the ith equation. So let's bring everything on the other side which does not contain xi and divide it by the coefficient of xi, which is aii, and call the resulting value xik plus 1. And do this for all I, and you end up with a vector xk plus 1. This is the idea of the Jacobi method. And in the next slides, I will tell you, so first of all, this is a very intuitive way of creating an algorithm. Just solve it. The idea is, if you have a triangular matrix, this is actually what you do. So if you assume that the matrix A is a lower triangular matrix, then this method here will give you the exact solution. So this is the idea of the Jacobi method. And in the following slides, I will show you how this can be reformulated into our setting, which will give us the general form will give us the matrix formulation of the Jacobi method, and you will see that this is actually a splitting method. To do so, we do a little bit of calculations. Don't be afraid. So first of all, in our definition, in this sum we do not have aii or xi containing, because this is excluded. Of course, it was brought to the other side. So just add it and subtract it again. So we have here a full sum kind of. Because this here is just the ith component of the vector a multiplied xk. And this value here is just the ith component of the vector d times xk. And if you made use of this, if you do this for all components, for all I from 1 to n, you end up with this vector formulation here. So xk plus 1 is d inverse of d, because the inverse of d contains just element, when d was a diagonal matrix, so it contains just the elements 1 over a ii. Okay, for simplicity, we assume that the matrix D is, of course, invertible. Bi will transform to B, and already mentioned, the second and this sum will give A xk, and this term here will give D times xk. So this is nice, because now put D minus 1 into the sum, and you will end up with this term here. And in fact, this is all we have to do to get our Jacobi method into our general framework of the splitting method. Because here you can see the splitting method again. Our splitting method was given this form. So here we have the Jacobi method. So if you set P to be the diagonal elements of the vector A, which is of course a approximation of A, and it's very, very easy to invert. Just invert the elements of the diagonal. And the resulting method is called the Jacobi method. The Jacobi method works best if the elements of D are dominating, meaning that the diagonal elements of D are very big compared to the other elements of A. This is called a diagonal dominant matrix, and this is used in the convergence analysis of the Jacobi method. But you can see that the easy choice of P to be equal to the diagonal elements of A give a nice method. This is actually, I think this is the first method you will learn in a school or in the university when it comes to splitting methods. The next method we want to take a look at is the so-called Gauss-Seidel method, which is a pimped version of the Jacobi method. Let's start again with our n-linear equations. You can see them here. And again, similar to the Jacobi method, we solve the ith equation for the ith variable. But instead of using the old vector, we use the updated vector for values j less than I. So what does this mean? Here you can see the Jacobi method, and we have a sum here containing only elements of the vector xk, which is the old version. But if for j less than I, we already have the updated values of xk plus 1 at hand, because we computed them right here, so just use them. The idea is, the more information we have, the better the algorithm will be. This is the general idea. So let's split this sum into two parts. You can see the first part here, which contains for j less than I minus 1, contains elements of the vector xk plus 1. And here you can see the rest. So the sum is just split into old part and already updated parts. Although this might look more complicated than the Jacobi method, when it comes to implementation, it is way easier than the Jacobi method. Why is that so? For the Jacobi method, I have to store two vectors, the xk, so the old version, and the updated vector xk plus 1. This is not needed here. You can store all values in just one vector, because if you have computed xik plus 1, well, just write it into the same vector, because we will use the old values here, so there is no need for storing it in a separate vector, which makes the implementation very easy. Okay, can we put this method into our general framework? We can, but we have to do a little bit of work here. So we make heavy use of our splitting A is D plus L plus U. Here you can see again the Gauss-Seidel method. And again, we reformulate this as a matrix vector formulation. So this fraction here will give, of course, the inverse of D, which contains just the diagonal elements. The red sum here contains just elements of the lower part of of the matrix A. So this sum here is exactly L, which is a strict lower triangular matrix, times xk plus 1, so the updated one. While the right-hand side, in a similar fashion, contains only element of the upper part of the matrix A, so this is just U times xk. U contains the upper elements, so the elements above the diagonal, if you remember it correctly. Now we have this matrix vector formulation at hand, and we can reformulate it now to fit into our general framework. This is a little bit of a lengthy calculation, but I put it here into detail because there's a nice trick and I want to show it to you. Let's start with this equation here. First step is to bring d to the other side. So we have d times xk plus 1 on the left hand side. And now we have an element xk plus 1 here and an element xk plus 1 here. So just put it on the left hand side, and then this thing looks much more nicer because we have now d plus l times xk plus 1 times b minus uk. So this is what's left here on this side. Assume that d plus l is invertible, bring it to the other side, and you will end up with this term here. And now here's a little trick to get our thing into our setting we want. Just add the stuff, add the vector we want and subtract it. So this is 0. So we do not change the value of, or do not change the equation here. So bring one xk in front, and the other xk is brought into this equation here, just by adding d plus l xk, because this cancels out with the inverse here. Just bring it into the term here. But now this looks much more nicer because what do we have here? We have d xk plus l xk minus u xk. So d plus l plus u, which is exactly a. So using the adding a 0, basically, this is just adding a 0. This is called adding a 0. We have formulated our Gauss-Seidel method into our general framework, which allows us now to see that if we choose P to be the diagonal matrix plus the lower part of the matrix L, we end up with the Gauss-Seidel method. You can compare it here. And of course, D plus L is a much better approximation of A than just the diagonal elements, which it was for the Jacobi method. So in fact, this is a much more better method than the Jacobi method, of course. The third and the last method I want to show you is the so-called successive overrelaxation method, or SOR method, which actually includes the Gauss-Seidel method as a special case. So again, here we have our n linear equations. We solve the IF equations similar to Gauss-Seidel. But now, in order to speed up the conversion speed, we add a combination of the old vector xk with the outcome of the Gauss-Seidel method. So here we can see we have the term coming from Gauss-Seidel, and we add a combination of the old vector, so I minus omega times xk plus omega, and the outcome of the Gauss-Seidel method. So if we choose omega to be 1, well, we basically end up with the Gauss-Seidel method. So this is a kind of extension of the Gauss-Seidel method, and omega has to be chosen correctly, and there exists a lot of analysis for this, how to choose omega correctly in order to get the fastest conversion speed. Can this be put into our framework? I mean, it can, of course. I will just rush through it because, well, the calculations do not differ that much. Again, we use our splitting. Here you can see the SOR formulation. And if you put it into a matrix vector formulation, we basically end up with, this is the term coming from Gauss-Seidel. And this, of course, will give us 1 minus omega times xk. Do a lot of calculations, and you'll end up with this term here. So xk plus 1 is xk plus omega times d plus omega L inverse. Again, if you choose omega to be equal 1, we'll end up exactly with the Gauss-Seidel method. So in terms of our splitting method, if we choose P to be chosen as 1 over omega d plus L, this will give us the SOR method. So the idea here is to put a weight on the diagonal matrix. This is the idea of the successive overrelaxation, and you can see it here in the approximation formulation of our matrix P. We have now talked a lot about how to put splitting methods into general frameworks and do a lot of calculations, but what are they actually used for? And mostly splitting methods are used as preconditioner, meaning we want to solve ax equals b, but instead of solving ax equals b, we solve p minus 1 ax equal p minus 1 b. So we reformulate the system, and again, p should be chosen as above as a good approximation of the matrix A. And a famous example is for instance, the use of the Jacobi method as a preconditioner in the conjugate gradient method in the context of solving equations which comes from the numerics of partial differential equation. The matrix there has a very specific form, which makes it very suitable for preconditioner, for instance, the Jacobi method. And this increases the speed of the conjugate gradient method a lot. I think I will do a video about this topic because this is very interesting. So usually splitting methods are used for preconditioners, either a left-hand side preconditioner or a right-hand side preconditioner. Doesn't matter. Okay, we are at the end of our video. Let's do a quick summary. Splitting methods, they can be used to solve system of linear equations, but mostly they're used for speeding up other algorithms, for instance, as preconditioner. The convergence, I mean, we haven't talked about convergence, but the convergence can be analyzed using the Banach fixed point theorem, and therefore it's useful to have a matrix vector formulation instead of the recursive formulation, because this is way more accessible than the other form. And most important, they can be understood as quasi-Newton method for solving an optimization problem, which gives a very good insight into the idea and into the structure and into the behavior of such methods. This is all I wanted to show you about splitting methods. There's a lot of way more to tell, but I want to put it in a nutshell. And I hope you enjoyed this video. If you have any questions, just write some comments or write me an email or whatever. Well, take care, have fun, and see you around.